Section 5.3, solving systems of linear equations with elimination. So we've already seen how to solve systems of equations using graphing and substitution. We're going to look at one other method today that may be useful. Let's look at this problem. Mr. Callan is taking his 4 cousins to the aquarium. First, he orders 1 adult ticket and 4 child tickets. Total comes to $42. But then the ticket seller is a little suspicious, tells him that the age for the child tickets is only 3 to 11. This means that Mr. Callan's 12-year-old cousin actually has to get an adult ticket. Seems a little young to be called an adult, but that's okay. This is going to raise the total cost to $44. So the question is, how much does each type of ticket cost? How much does it cost for an adult ticket? How much for a child ticket? So what we're going to do here is we're going to look at this to set up 2 different equations to talk about the 2 different scenarios. First, we have the initial scenario, where I ordered 1 adult ticket and 4 child tickets for $42. Well, you can choose whatever variables you want here. If you want to use X and Y, that's fine. I like to use variables that make sense. So I'm going to use A and C to represent adult and child tickets. Now, if I'm ordering 1 adult ticket, I'm going to put the 1 there, and I'm going to multiply that by A, because that's how much I'm going to spend on the adult tickets. 1 times however much each adult ticket costs. And then I'm going to get 4 child tickets. So I'm going to add 4C to that. If it's 2 child tickets, or it's $2 per ticket, that's 4 times 2, which is $8. But I'm not sure exactly how many I'm getting yet. Now that gives me a total, which equals 42. Okay, so that's my first equation. My second equation is going to come from the second scenario, where one of my cousins, who's 12 years old, actually is getting an adult ticket. So now instead of 1 adult ticket, I'm getting 2. So 2 adults. And one of the 4 child tickets before is now going to be getting an adult ticket, so that's down to 3 child's tickets. And that has raised the cost up to $44. Okay, so when we look at this here, I have 2 equations. Now, I don't have X and Y, so I'm not really sure how I would graph this. Substitution is a possibility, but I want to look at it one other way. So let's see now how we can solve this system using this new method called elimination. You can see here I've rewritten my 2 equations, 1a plus 4c equals 42, and 2a plus 3c equals 44. The 1 may be unnecessary in front of that a. I've put it there just to emphasize where it came from. But if you just want to write a plus 4c equals 42, that will be fine. To use this elimination method, what I do is I multiply one or both equations by any number that I choose that will set up a pair of terms that are opposite. So I want one to be positive, one to be negative. So what I mean by that is I'm trying to look at the A's or the C's, and I want to get them so that they're opposite. I want one to be positive 7A and negative 7A, or positive 10C and negative 10C. So I just have to pick out a way that's going to be convenient to get there through multiplication. You can choose whichever method you want. You could multiply just the top one by negative 2, because when you distribute that negative 2, it's going to create a negative 2A, which would be the opposite of a 2A. Now, that's how I would probably do it myself, but just to kind of show you with a little bit more practice, I'm going to choose to do it a different way. I'm going to choose to look at the C's, and I want to make the C's opposite. So I think about 4 and 3 and think, what do they both multiply to? Well, I can get them both to get to 12 if I multiply carefully. So I'm going to multiply my first equation in order to get it to be 12 by 3. Now make sure that everything gets that 3. So that's going to become 3a plus 12c equals, and you have to do 3 times 42, which ends up being 126. All right, that's a big number, but not unmanageable. Now for the other one, I have to get the C's to cancel out by being opposites. Now that means I'm going to be multiplying still to get to 12, but not just 12. I actually want to get to negative 12. So I'm going to multiply this one by negative 4. So when I distribute that, that brings me to negative 8a minus 12c equals negative 176. Okay, so now I've got these two new equations. Well, that doesn't seem very helpful. Well, here's what we do. I'm going to look at this, and they're lined up in columns. The 3a and negative 8a, 12c and negative 12c, and 126 and negative 176. They're like terms as they're lined up. So what I'm really doing is I'm adding these two equations together. And when I do that, it's going to create a new equation. 3a plus negative 8a is negative 5a. 12c plus negative 12c, that's been canceled. That's been eliminated, which is how we get the name of this process. And then finally, 126 plus negative 176 is negative 50. Well, now I have a really easy equation left to solve. If I divide each side by negative 5, I get a equals 10. The adult tickets cost $10. All right, so now I'm on track. Now that I figured out that answer, I'm going to take a equals 10 and I'm going to plug it back into either one of my original equations to get my answer for C. Plug it into either one, it doesn't matter. I'll plug it into the bottom one. 2a becomes 2 times 10 plus 3c equals 44. 2 times 10 is obviously 20. When I now subtract 20 from each side, I'm going to get, oops, sorry, I got ahead of myself there. That's not 24, that should be a 44 there. So when I subtract 20 from each side, I get 3c equals 24, which means that c equals 8. So the children's tickets cost $8, the adult tickets cost $10. I can check my work just by going in to my two equations. One adult ticket plus 4 child's tickets, that would be 10 plus 4 times 8 is 32. 10 plus 32 is 42. And 2 times 10 is 20 for adult tickets, and 3 times 8 is 24. 20 plus 24 is indeed 44. So that's how you do it. You just follow those 5 steps, and you'll have your solution. Oftentimes, we'll write our answer as an ordered pair, x and then y. If we have a word problem, we'd probably write it out as a sentence. In this case, something like adult tickets cost $10 and child tickets cost $8. All right, so there we go. Let's take a look at our two special cases now. All right, so kind of like before, we have our two special cases. The last one was a normal system of equations where the two lines intersect exactly once. And so what we need to look at now is what happens if it's one of those other two cases. So go ahead and try using the elimination method on these two. And when you get to the end of the first couple of steps, I think you'll see something interesting has happened. We'll come back and talk about them. So pause the video, try to solve them, and then come back and check your work. All right, how'd you do? All right, so when we do this, and you could have done each one of them slightly different, but this is probably the easiest approach. With the first one, I ended up getting 0 equals negative 8. And for the second one, I get 0 equals 0. This should look pretty familiar based on what we talked about with substitution. When we have something like this, we have a statement that is false, 0 equals negative 8, and a statement that is true, 0 equals 0. What we saw yesterday is that a false statement indicates that these lines are parallel, there's no solution. A true statement indicates that these lines are actually the same line and there's infinitely many solutions. And so that's what will happen when we're using elimination and we end up with a special case. Most of the times we'll have a consistent independent system, so we'll just have one solution. But if all the variables cancel out, whichever one we were trying to target, they end up both canceling out, most likely we've done it correctly and we have a special case. There's no ordered pairs that will make both equations in the first problem true, and there's a whole bunch, an infinite number in fact, that will make the equations in the second problem true because they're the exact same equation. All right, so I hope that this makes a lot of sense and that now you feel comfortable using elimination to solve systems of equations.